Okay. Am I back on? Okay, there, finally live. Okay, so last time we left off, we were talking about basic arrays. These are what's actually more technically referred to as static arrays. And the syntax for declaring a static array is what are the type of elements you want. Again, it has to be uniform. The name of your variable, bracket, and then the size. So like, for example, down here, AR2, which has 10. You can also do an initialization list by saying equals and then the values inside curly brackets. If you don't list the size here, but you do an initialization list, it will default to being as big as the number of elements that are here. So 1, 2, 3, 4, 5, 6, 7, 8. So doing 8 or leaving nothing there is the same as long as you do an initialization list. If you just declare an array, like you can do like int AR or whatever variable name is, bracket 7, that makes spacer 7, the values are uninitialized. They're not set to anything, perfectly okay, perfectly valid, and makes lots of sense. As you can see, arrays don't really have a way for you to figure out the size of them, so you have to keep extra variables around to track their size. For example, AR1 length or AR2 lengths. You just have to keep these things around. You might see pieces of code online where someone does like the size of AR1 divided by the size of an integer. That does not work in all cases. It works in an extremely limited number of places. Never ever use it in the class. It'll probably screw you really good if you do use it when it's actually useful. So just keep that extra variable around to keep track of its size. If you want to index a variable, for example, we have this function over here which just prints an array. To access an array, it's bracket index, just like in Python. No negative indexes though, so you can't get the last thing by saying -1 or the second to last thing by doing -2. That'll put you out of bounds and give you a seg fault if you try indexing at a negative number. So don't do that. And again, it's 0-based indexing. So your first element's at 0, then 1, then 2, then 3, then 4, and so on. Any questions so far about the basic arrays? Yeah. Yes. So no, like with these static arrays, when you declare their size, which has to be known at compile time, so basically needs to be a constant, they are that big. They get no bigger, they get no smaller, right? There can be things like with AR2 where I declare space for size 10, but only use the first 3 elements, right? Which, you know, you might want to do then like AR2 len is actually probably equal to 3 because I'm only storing 3 things in it, right? You're generally keeping track of the number of elements you have contained, not what its actual length is. So the question is, what if you don't know how big it needs to be? There are 2 options. One is you don't use static arrays, which is probably your best option, and you have to use pointers, which we'll talk about in a couple minutes. If you're really dead set on using static arrays, you make a number that's big enough to hold the largest amount of input you'll ever need to receive. That's generally a very bad way of doing things, because how are you ever going to be guaranteed that the input will not be any larger than that? If it is, it's going to break things. The other thing is, if the input is much smaller than that, you're wasting a lot of space. So not a good way about doing it, but that's how you do it if you want to stick with only using static arrays. Any other questions? You can do multi-dimensional arrays statically. You can go up to any number of dimensions you want. You just list the size of each of the dimensions. So this is a 4x4. Or if I want to do like a bracket 4 by 5 by 20 by 16 by 32, completely legal. Nothing wrong with that. The thing is, though, is if you're working with a statically declared matrix, when you're trying to pass it as an argument to a function, you have to specify the size of all of the dimensions, how much space you actually made, except for the first one. So here you can see for a matrix printer, I have to specify how big the second dimension is, all the dimensions but the first. And so like if you wanted this function to be able to work with like every single type of matrix, you would actually have to have a different one declared for each one for the number of elements per row, which seems kind of stupid, right? If you want to know why that's the limitation in C, come talk to me in ECS 50 and we'll discuss why the static arrays have to have all the dimensions but the first specified and the parameter list. So if you want to write functions that work with like any number of elements per row, well, you're going to have to use a dynamically sized array, which we'll talk about in a little bit how to do that. But notice I had to list that parameter there. Here's another example of having a matrix as a function. So here, this is going to make the identity matrix, which is a 1 along the main diagonal and zeros everywhere else. So I go through each row, I go through each column. If the row matches the column, I set the value to 1. Otherwise, I set the value to 0. So like indexing a multidimensional array is not really any different. One of the things to note, though, is you cannot return these static arrays from a function. We'll talk about later why you can't do that. But the thing is, like when you get normal arguments to functions, right? You get a copy of their value, right? This is called call by value. So if I have some function that's going to take some integer, I get a copy of that variable's value when I pass it in, right? This is why pieces of code like this, you know, void do nothing. Right, this piece of code is kind of useless because after the x and y's are copies of the variables that I passed in. So here I'm changing this local variable x and not the actual parameter I passed in. So if I did something like this, oops. If I did something like, you know, int a equals 7, b equals 10, and then I called do nothing, AB, what's the value of A going to be after this? Still going to be 7, because again, we got a copy, right? X is a copy whose value was initialized to 7. With arrays, kind of probably like you're used to in Python, right? In Python, if you mutate the value of an array inside of a function, right, like you assign a value to it, or you append to it, or you insert into that array inside of a function, right? You notice that change happened outside the function as well. Same thing holds true here in C because you're actually getting a pointer to the elements, and we're going to be modifying the memory and address. So here, even though I can't return the matrix, I can still initialize it, and then after the function is done running, you'll see that the values have all been filled into the original. Any questions? So when you get copies of variables, that's called call by value, because you're getting a copy of the value whenever you call the function. And if we ran this, first thing that we do is we try to find some of these values in these arrays. And you know, we find the first 5 is at index 1 of the array. We found the value -2 at index 4. We searched for -99 in the first array. It's not there. We searched for the value 17 in the second array. We didn't find it. We create our matrix and we print it out. And then again, I called make identity matrix, which then made it the identity matrix. 1's on the main diagonal, 0's everywhere else. And then we print it out. Good. One more pit stop, and then we'll get into pretty pictures and pointers. So you guys have all seen casting in Python, right? Where you can do like the int of a string that represents a number, or you can do like the int of a double. When you did the int of a double, what would happen to the value? If I did like the int of 35.72, I would get just 35, it rounds down. So you can do casting in C as well to change between the types. It's just not nearly as flexible. Pretty much you can cast between any of the numeric types, so between doubles, integers, and characters, but you can't just say, oh, I have this, number 35.72, I want to cast it to a string. That does not work. You have to use a different function to make that happen. And there's two types of casting. There's implicit casting, which is casting the compiler does on your behalf. And then there's explicit casting, where you say, I would like to cast this variable to some other type. When you do the cast, it makes a copy of that expression, but in the new type. So an implicit cast will happen when you do a variable assignment. So like if I have my integer x and x is assigned some expression, that expression's value will be cast to an integer before it's stored in x, because x can only store integers. Or if I have a double, right, and I assign it to some expression, that expression will be cast to a double before it's placed into my double variable. Because doubles can only store doubles, integers can only store integers, characters can only store characters, so the types will be cast whenever you do an assignment, if the type is different than the thing on the left-hand side. You will also see cast will happen when you call a function, and the type is different than the one that's specified. So you might have some function that accepts doubles. You can pass it integers. Those integers will be cast to doubles before they're passed into the function. And then, again, the casting can be done pretty much between all the numeric types. Again, char, double, float, integer, but it can't really be done between strings. And if the cast cannot be done, you'll get an error. I'll say, nope, you can't do that. It's also kind of helpful with this explicit casting with doing the, you want to do arithmetic in the floating point realm, but you have integers. Normally you're doing like division. To cast, what you say is new type, the new type that you want in parentheses, and then you list the expression on the right hand side that you want to cast. Generally casting has pretty low precedence, so you might need to do some additional parentheses to make the casting happen at the correct time. So you can do something like, I want to cast 70 into a character, so char. Or I want to do 63 divided by 29, but instead of doing like 63 divided by 29, I'm getting something like 2, right? I actually want to get the decimal value. I have to cast it to a double first. So I do the division between the two doubles. And again, just like in Python, if you cast a double or a float to an integer, you lose the values that come after the decimal point. So here's just a simple function that takes x and y and returns their sum, but you notice it takes everything as double. And then here's two simple functions that calculate the percent of pizza eaten. One does things the correct way, the top one. The other one does the things the bad way. So the problem here, so the first one, right, we make sure that we cast the numerator to a double, and then we ensure that we cast the denominator to a double, and then we do the division. So it's double over double, and our result will be a double, and we'll give back that double. If we're over here in this bad version, right, both these guys are integers, so we're going to do integer over integer, and then take that result, which again, if we're doing some percentage, it's going to be some number over some number. It's probably going to be 0, because some percentage is going to be between 0 and 1. Like if I ate like 7 out of the 10 slices of pizza, right, 7 divided by 10 is 0, then that result will be, before it's returned, cast back into a double, and so it'll turn from 0 to 0.0, and we'll return that. So yeah, just be careful when you're doing your casting. So some examples over here. I didn't quite finish printing these out. Okay, So this first example is showing the implicit casting happening with the add function, right? X and Y are both integers, but the function y doubles. So before we cast the result, or before we pass X and Y into there, the compiler will implicitly cast both X and Y to doubles, then pass the double version of the variables into the function. And then when we return the value, right, it's going to be a double, but because Z is an integer, the result will be cast back into an integer before it's stored into Z. Does that make sense? Any questions with this first part? Okay. So line 75, what do you think it's going to print out? So we called DPPE1 is percent pizza eaten with X and Y. X being 6, Y being 10. Yeah, 0.6. What do you think the second value going to be printed out is going to be? 0.0, right? 77? 0, right? The reason why this one's 0 is, again, we still use the good pizza percent function, right? And so we get back 0.6, 0.6, but the value has to be stored into a integer. So when we store it to an integer, it has to be cast back to an integer. So we discard the decimal part, and we're left with just 0. And then again, IPv, the second one, we just did the bad version. So we're going to get back 0.0, which we then transform back into 0 and store the 0. Does that all make sense? Any questions here? Yeah. Yes. So you want to take 100 times this. So I ask you, what do you think is going to be returned? 0. Because we do the division first, right? Right, we do the division first, so we do something like 6 divided by 10, that's 0. 0 times 100? 0. So you still get back 0. So if you did 100 times num slices eaten, we'd get 60, or we'd get 60 over 10, and so you'd get back 6, which is not really like a good percent. So the question is, if I only cast the numerator or only cast the denominator to a double, would the result be a double? Yes, it would be. Because again, remember, integer and double arithmetic brings it into the double realm. Any other questions? Okay, it's pointer time. This is not pointer, so don't worry. Okay, so the big thing with pointers is that well, we'll get to this in a second. First, I want to do an analogy. So let me know if this helps you think about memory and things like that. This is memory lane. On memory lane, we have a whole bunch of empty lots where people can build. Oh, it's not showing. Oh, the little screen over here is broken. You can see that, right? Okay. This is memory lane. Over here, we have a whole bunch of lots where people can build houses. These lots have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, and 12. These lots correspond to the individual bytes inside your computer system. These are things where you actually store values in memory. And the unit that you access memory with is a byte. It's 8 bits. Now, when people are building their houses over here on memory lane, they might want houses that are only 1 lot big, which is perfectly fine. Someone might build a house over here on lot, oh, not lot 0. Someone might build a house over here on lot 1, right? But some people might want larger houses, so they build larger houses over multiple lots, right? This guy might want a house of size 4. This guy might want a house of size 2, and so on, right? When we're using these lots to build houses, this is when we're asking the computer for space for our variables, right? And different variables have different sizes. For example, sounds like it went off, right? Hello? It still has battery. Hello? Hello, 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 hello. Come on. Back on now? There we go. The volume went to 0 for some reason. I don't know why. So, for example, a character is 1 byte big. Or an integer might be 4 bytes big. So each of these variables occupies some number of bytes within memory. Everybody cool so far? Any questions? Okay. So what we can do is, people might move into each of these houses and they might, put things inside their houses. For example, this guy might have letter A. This guy might have the value 27. This guy might have the value 64, right? So the space that we have for the variables, right, is in the individual bytes, and we're going to be able to put some values there to store for later on, right? So this guy we might nickname as C. This guy might be num. This guy might be snum. So when we ask for a variable, like we say integer x or integer num, we ask the compiler to make space for 4 variables, and then if we initialize it, this is num equals 27, we're saying, hey, compiler, go make enough space for an integer, and then initialize its value to 27. Or if we just say something like, this guy over here, I don't know, E, if we just say a short, is a type you haven't seen, but short's 2 bytes big, short E, right, that just says, make some space for this house, make some space for this variable, but don't put anything inside of it. We all cool? So you can see that each of these houses also has a location of where it's stored at in memory. That's its address. And for these houses that are multiple bytes big, the starting point of the house is its address, right? So something like the address of C is 1. Address of num 2. The address of snum is 6, and the address of E is 8. Does this all make sense so far? Good. So the operator that we use to get the address of some variable is the ampersand operator. So if we do ampersand C, that's 1. Ampersand num is 2. Ampersand snum 6. And the ampersand E is equal to 8. So again, when you do the ampersand, you're asking for what is the address of this variable. Does that make sense? Every variable has some address, where it's located in memory. Every variable has a value, something that's stored inside of it. You can't do something though like this, like what's the address of C? Doesn't really make sense to ask, right? You know, if you ask for the address of C, well, C is located at location 1. Then we're like, well, what's the address of location 1? It doesn't really make much sense, right? So this is like illegal syntax, and you can't do it. And you might be tempted to make the types match, but it doesn't work. So ampersand is the address of. We can also declare variables to hold addresses. And a variable that holds an address is of type pointer. It's a pointer. So the way that you declare a pointer is type star variable. So for example, if I want to be able to point to num, so we said as an integer, we do something like int star num equal to address of num. So now pnum holds num's address. Does this make sense? So over here we've created a whole new variable. We created a whole new variable. Over here pnum. And what value did we put inside pnum? 2, right? It's the address of num. So this guy just had the value 2. And you can really think about like pointers, all they really are doing is holding numbers. These numbers just tell you where something is at in memory. That's it. Or if you like drawing things out, you can say something like pnum points to num. Right? It's not C syntax or anything, but pnum is currently pointing at num. That make sense? Any questions? Yeah. Yeah, some people like to put the star here, some people like to put the star here. You could probably even put the star in the middle and it still work. You can see white space doesn't matter. I prefer my star on the type because it's just easier for me. So I think about it. I think about this is my type. Some things people also say that help making work with pointers easier is if you read the type from right to left. So pnum is a pointer to an integer. Right? Or if I said something like this, star P equals the address of C. You can say CP is a pointer to a character. Make sense? Any other questions before we keep going? So how do you get the address of where a variable is at instead of its value? Ampersand, variable name, right? Ampersand is the address of. Give me the address of C. If I just want C's value, C, right? And when the compiler sees these variable names, they're just like nicknames for where these things are stored at in memory, right? So you might say, go to the old Webster house, right? Or I'll see you at the library. These are all just nicknames for where these things are located in memory. So every time the computer actually is like working with C, it's like, oh, well, C is at address 1, so that's where I want to put my information, at address 1. Or when I see num, I want to go to address 2 and do something at that location. Or if I say CE, I want to go to address 8 and do something there. But we give these nice nicknames to things to help us be easier for us to think about, not the compiler. But the compiler will just translate them to a raw address at the end of the day. Any other questions? Yeah. Pnum does have a value. It does store something, right? It holds the address of num. What do we say the address of num is? 2. So what value does pnum have in it? 2. Yeah, so if you printed out pnum as an integer, you would see 2 in this example. In general, the values are going to be a lot bigger than that. But yes, it's just some location. What's the index of the byte where this thing begins at in memory? And the indexing starts at 0. So all pointers store addresses, whether they're double pointers or integer pointers or float pointers or short pointers or whatever pointers. They all store addresses. So this guy right here, he's storing the address of C. So CP's value is equal to 1. It's a pointer, it's an address of. Right? It's the address of something. So yeah, but the addresses are numbers, they are integer numbers, but like integer and pointer aren't like necessarily like directly castable or interchangeable inside of C. But yeah, it just has the value 1 in it. You can store the addresses of anything. The address of a double, the address of a character, the address of yeah. So your question is like, why do we have a separate type for like a pointer type? It's generally, there are a couple of operations that are, there's one operation that's defined on integer or on pointer types that are not defined in integers, such as the dereference, which we haven't talked about. And also having these separate types helps us think a little bit clearer about things, right? Yes, addresses are just numbers, but if I'm saying, okay, this thing is a pointer to something, right, then I know I'm actually referring to some location memory, right? Like my pointer has the address 100 in it, I know I'm actually going to work with address 100. Versus this variable has the value 100 in it, I'm probably working with the number 100. If we use the same type for both, it would be hard to distinguish between what our intent was. You can cast pointers. There's no issue, and basically any pointer type is castable to any other pointer type, but be careful with your pointer casting and making, being very, very careful. You can screw up pretty easily if you're doing that. Yes? Yeah, I mean, like, because the double ampersand is like a boolean, there's logical and, right? So it's like, you're doing what and C. It wouldn't work because of that reasons, but even if it, like the ampersand wasn't used to denote boolean and, it still doesn't make sense. It doesn't make sense to like ask what's the address of the address, right? Like I can ask what's the address of this house? Like what's the address of UC Davis? It's 1 Shields Avenue. What's the address of 1 Shields Avenue? That makes no sense to ask, and that's what you would be trying to do. So like when you declare any type of variable, right, you're making space for it, right? And inside this variable, we are holding the address. Think, for example, like when you send some snail mail, right? Your envelope holds the address that you're trying to send it to, right? It also holds the address of where you sent it from. If you want to think about it that way, right? So it's okay for things to hold the addresses of buildings in real life. Same thing here. We can't hold the address of variables, but right, it's going to take some more space to do it, right? We needed that envelope to be able to write it on. We needed this section in memory over here to hold pnum. Oh, pnum has an address. What's pnum's address? We said that for things that are multiple bytes big, its address is where it starts at. So the address of pnum is 10. Oh, sorry. So the address of pnum is 10. It does live at memory address 10. And you can do things like this. Yeah, okay, integer, pointer, pointer. So I created a pointer to a pointer. So you can now think like this, like pp points to pnum, points to num. Right? There's just like this trail of directions to getting to some location memory. And if you read it from right to left, PP is a pointer to an integer. So you can think about it that way. The other thing that you can also think about is like the ampersand adds 1 star to the type of the variable. So when you put an ampersand in front of a variable, it adds a star to its type. So if we think about num, what's num's type? Num's type is an integer. So ampersand num, we add 1 star to its type. So the type of this expression is an integer pointer, right? A pointer to an integer. Pnum's type is an integer pointer, right? So you have an integer pointer on the left-hand side, integer pointer on the right-hand side, the types match. So one thing that you can help do to double check yourself is like, do these types match? If this is going to work right. So this is an integer pointer, this is an integer pointer, types match, we're good. Or look at C, C's type is integer, or C's type is character. So ampersand C's type is, again, it adds 1 star to the type. So ampersand C's type is char pointer. And we have a char pointer on the left, so again, types match, great, we're good. If we look over here, pnum's type is an integer pointer. So the address of pnum is an integer pointer. And pp's type is an integer pointer. Types match, great, we're good. Right? So make sure the types do match. Yes? The question is, how is holding the address, so how does a pointer to a pointer make sense? Because PP is not storing the address of the address, it's storing the address of pnum. Pnum does live somewhere. Where's pnum live at? At 10. So PP, its value is equal to? It's equal to the address of pnum. Where's pnum at? 10. So I'm holding, where is pnum located at in memory? I'm keeping track of this variable over here. Or pnum is keeping track of this guy over here. Right? No, pnum is a variable. It lives somewhere. Right? So I'm holding the address of pnum inside pp. I wanted to know where the address of pnum is at. There's this variable. So I'm not holding the address of this. I'm holding the address of pnum, which is located at address 10. What do you mean, can you point to the name of the variable itself? So can you do something like, the name of a variable itself really isn't stored anywhere. So like when your program is running, the name of the variable is discarded. All we deal with is raw memory addresses. And again, the variable names are only used by the compiler to translate them into those addresses. It's not stored. No, if you have like an integer pointer, like let's say it's like 4-pointer, right? It can hold the address of a triple pointer. That's it. You mean down here when I drew the arrows? Well, I mean, I can use pp to get to pnum, and then from pnum I can get to num. But pp has no idea what num is, like where num is at. It has to go through the layers. Yeah, it's not pointing anywhere. Anything else? Yeah. Yeah, absolutely. All right, I can do something like, I'm going to flip pages in a second, but we can do something like integer pointer alt p equals pnum. What value is in alt p? What value is in alt p? So is it 10? Is it 2? It's 2 because we said alt p equals pnum. What value did we say was in pnum? 2, right? And so pnum is just a standing for its value, 2. So alt p is also equal to 2, which means alt p also points to num. Again, I'll show that in a second. So again, we said something like, here's our variable, here's its value, here's its address. So here we had num. It had some value, we said like 27, and its address was at location 2, right? Then we did this line of code, integer pointer pnum equals the address of num. This creates a new variable, pnum, whose we said was located at address 10, and pnum gets what value? Num's address, which is 2. Then we said integer pointer alt p equals pnum. So I create alt p. It might be, let's say it's at address 16. What value is it going to get? 2, pnum's value, right? You know, if I said something like this, you know, integer y equals num, would you be confused about what value y is getting? Right? So we like create some value y. It might be at an address 20, and its value is going to be 27. Again, like the values for the addresses are all made up. If I were to drop num, so if I got rid of num, I guess your question is if num is deleted, are the other pointers to it automatically updated? So if you delete it, assuming you dynamically allocated it, the pointer values aren't going to change, right? So they're not automatically updated when something gets deleted. Anything else? So there is one other operator. It's the dereference operator, and you do something like this. It's star and then some pointer. What this means is go to the address, equivalent to, go to the address held by pointer and get the value there. So if I do something like star pnum, this means go to where pnum is pointing to and get the value that's there. So pnum, where's it pointing to? It's pointing to address 2. Then go get the value that's there, 27. Right? If I say star alt p, this means go to where alt p is pointing to, go to that address, and get the value that's there. So we go to where it's pointing to, which is its value, that's what it holds. So we go to also address 2, get the value that's there. It's still 27. Or again, if we have something like this, integer pointer pp equals the address of pnum, this would create a new variable pp, who might be located at address 30. And what value does he get? now if I say star PP, what am I going to get? So again, it just says go to where PP is pointing to. Where's it pointing to? 10. What's the value that's there? 2. That's all the dereference operator says to do, is to go and get the value that's there. You can dereference a variable as many times as it has stars in its type. So for example, pnum can be dereferenced once because it has 1 star in its type. Alt P can also be dereferenced a single time because it has a star in its type. PP can be dereferenced twice because it has 2 stars in its type. So I can do star star PP. So again, take it one step at a time. The first thing that we want to do is star PP. We want to get the value that's there. So again, star PP, go to where it's pointing to, address 10, and get the value that's there, 2. So then we say, go to this location of memory, 2, and get the value that's there, which is 27. Does that make sense? Yes. I'm not. You want to write like star 2, like you want to do like this star 2 PP. So we'll continue talking more about pointers on Wednesday and actually do something useful with them. But hopefully they're not seeming too crazy or too complicated yet. They just hold addresses.
Could you give me that paper? I'm gonna scan it and put it on.
Thanks.
Professor Hunter, can we go out this door?